Hello everyone. So this is the second tutorial session on cylindrical wave functions. Okay. So the first question says that we have a circular waveguide and the dominant mode cutoff frequency of 9000 megacycles. So what is its inside diameter if it is air filled? Okay. So the cutoff frequency is for the circular waveguide is given as 9000 megahertz, that is equal to 9000 into 10 to the power 6 hertz. Okay. Now in the question it is said that it is in the dominant mode operation. Okay. So for circular waveguide, so it is given like we have the dominant mode. Okay. So and the dominant mode is, we know it's TE11. Okay. So now we need to find out the inside diameter if the circular waveguide is air filled. Okay. So for dominant mode, lambda c TE, we can write it down like 2 pi a upon x n rho dashed, where a is the unknown that we need to find out. Okay. So we can write for TE11, we know x n rho cap is given as 1, x n rho dash is given as 1.841. Okay. So we will have then lambda c TE as 2 pi a upon 1.841. Okay. Now we can also write lambda c as 3 into 10 to the power 8 upon, that is c by f. So f is 9000 into 10 to the power 6, that gives us 1 upon 30 meter. Okay. So that is 10 upon 3 centimeter. Fine. So therefore we can write 2 pi a upon 1.841 as 10 upon 3. So then we will have a as 10 multiplied by 1 upon 841 divided by 2 pi multiplied by 3. So this will give us 0.977 centimeter. Okay. In the next question we need to calculate the attenuation constants due to conductor losses in a circular waveguide. So for finding out the attenuation constant, we will consider both the modes, that is for TM modes and TE modes. So to start with TM modes, we can write for TM modes we have psi of Tm as Jn k rho cos of n phi e to the power minus j k z z. Therefore, from the fields that we had previously, we found out that E rho is given by 1 upon y cap del square psi upon del rho del z. So, this will be 1 upon y cap del rho of. Okay. First, with respect to differentiation with respect to z. Okay. So, we will have Jn k rho cos of n phi e to the power minus j k z z minus j k z. So, this will give us 1 upon y cap. Now, with respect to rho, so it will be Jn prime. So, this is Jn prime k rho minus j k z cos n phi e to the power minus j k z z. Okay. So, this is E rho. So, let us give this equation as equation number 1. Now, again E phi. So, E phi we will have E phi is 1 upon y cap. We had previously we had E phi as for Tm modes, we had 1 upon y cap, then 1 upon rho del square psi upon del phi del z. So, this will give us 1 upon y cap rho del phi of, at first with respect to z. So, this will be Jn k rho cos of n phi e to the power minus j k z z minus of j k z. Now, with respect to phi we need to differentiate. So, we will have 1 upon y cap rho. Okay. So, this will be Jn k rho. So, differentiating cos n phi, it will be minus of sin of n phi n e to the power minus j k z z minus of j k z. This is equation number 2. Now, h of rho. So, h rho we will have 1 upon rho del psi upon del phi, and this will have 1 upon rho. So, with respect to phi we are differentiating. So, it will be Jn k rho So phi, this will be minus of sin n phi n e to the power minus j k z. This we can write it down as minus, this minus will come outside. So, minus n upon rho, this will be j n k rho sin of n phi e to the power minus j k z. So, this is equation number 3. Now, h of phi is minus of del psi del rho, that is equals to, so with respect to rho, so we will have minus of, so j n prime k rho cos n phi e to the power minus j k z z. So, this is equation number 4. Now, to find out the attenuation constant, in the question we have asked to find out the attenuation constant due to the conductor losses. Okay. So, the attenuation constant due to the conductor losses, we can write this down as alpha, gives us alpha is P d upon twice P of f, where P d is the dissipated power and P f is the power flow. Okay. So, where P d we can write as, we know P d we can write in as r. So, integration will be from 0 to 2 pi rho d phi, and here we will have h rho square plus h phi square at rho equals to a and z equals to 0. So, h rho and h phi are known. So, we can just simply substitute and calculate P d, whereas power flow P f is given by integration of 0 to a rho d rho, that is E cross H star. So, integration will be from 0 to a rho d rho, 0 to 2 pi d phi, and this will be E rho H phi conjugate minus E phi H rho conjugate. So, again E rho H phi and E phi H rho are known. So, we can again substitute, and then calculating P d and P f, we can get the attenuation constant as P d upon twice P f. Okay. So, next for the TE modes. Okay. So, for TE modes, we have psi of TE as Jn k rho cos of n phi e to the power minus j k z z. So, E rho we will have, we know E rho is given by minus of 1 upon rho del psi del phi. So, we can calculate this. So, we will differentiate with respect to phi. We will have, so cos n phi will be minus of sin n phi. So, this minus and minus becomes plus. So, 1 upon rho, and then we will have g n k rho, this will be sin of n phi multiplied by n e to the power minus j kz z. So, this is E rho. We can give this as equation number 5. So, after E rho we will have E phi. So, E phi we have as del psi upon del rho. So, with respect to rho we will differentiate. So, we will get J n prime k rho rho, then k rho. So, this is cos n phi e to the power minus j k z z. So, this is equation number 6. Now, H rho. So, H rho we found out that H rho can be written as 1 upon z cap del square psi upon del rho del z. So, that will give us 1 upon z cap del rho of. So, first we will differentiate with respect to z. So, we will have J n k rho cos of n phi e to the power minus j k z z minus of j k z. And again with respect to rho we will have 1 upon z cap. So, this will be j n prime k rho, this will be again k rho, and cos of n phi e to the power minus j k z z minus of j k z. So, this is equation number 7. So, H rho and then H z. So, similarly we will calculate H of z and then we get H z as 1 upon z cap j n k rho square cos of n phi e to the power minus j k z z. Okay. So, again to find out the attenuation constant we need to find out P d and P f. So, power dissipated P d can be written as R. So, integration will be from 0 to 2 pi rho d phi, then h phi square plus h z square at z equals to 0 and rho equals to a. And power flow P f we can write integration of 0 to a rho d rho 0 to 2 pi d phi, then we have E rho h phi conjugate minus E phi h rho conjugate, and thus we can find the attenuation constant. So, h phi, h z, E rho, h phi, E rho, and these are all known quantities. So, on substituting we will get attenuation constant is the ratio of P d upon 2 P f. Okay. So, this is all about the cylindrical wave functions. Thank you.